This video is for topic 5.8, reaction mechanisms and rate laws. The objective for this topic is to identify the rate law for a reaction from a mechanism in which the first step is rate limiting. So we talked about how the slow step of a reaction is always going to determine the rate. So when we see a reaction mechanism and we have the steps listed out, the slow step is what's going to determine our rate law. So in this particular reaction, our overall reaction is 2A plus B produces X and Y. And this tells us that our slow step is the first elementary reaction. A plus B produces X plus M. Since this is an elementary reaction, our rate law is determined by the reactants raised to their coefficients. So that's how you write the rate laws for elementary reactions, and reaction mechanisms are made up of the individual elementary reactions. So since our slow step is our first one, that means the rate is K, which is the rate constant for that particular elementary reaction, times A raised to the first power because the coefficient is 1, times B raised to the first power because the coefficient is 1. So let's look at a different type of question. So this particular question asks us to look at three different options for mechanisms, and it asks us to decide which are consistent with the rate law. So our initial reaction is two NO2s producing two NOs and an O2. And it tells us that the rate for our overall reaction is NO2 squared. So we need to look at which of these reaction mechanisms gives us that rate law for the slow step. So reaction mechanism 1, the slow step is the first one, the first elementary reaction, and the rate law for that elementary reaction would be NO2 squared because the two reactants are two NO2s. So that one is consistent. So 1 is consistent. If we look at proposed mechanism 2, our slow step is still the first step, but in this mechanism, our slow step is 1 NO2 producing N and O2. So the rate law for this elementary reaction would just be K times the concentration of NO2, which is not consistent with the rate law. So that one does not match. Mechanism 3, our slow step is also the first step. And the elementary reaction is NO2 producing NO and O, which means that the rate law for our first elementary reaction would be rate equals K times the concentration of NO2. So that one does also not meet our rate law. So the only one that is consistent is reaction mechanism 1. Notice that all of these mechanisms are valid based on how the reactants turn into products for the overall reaction. However, the mechanism must be consistent with the proposed rate law. And so the rate law is K times the concentration of NO2 squared. The only reaction mechanism that has an elementary reaction for a slow step that matches that rate law is proposed mechanism 1.
This question has us looking at the equation 2NO plus Br2 forms 2NOBr. And we have a set of experimental data, so let's look at the questions. Question A says to calculate the initial rate of disappearance of Br2 in experiment 1. So looking at our reaction equation, Br2 disappears at half the rate that NOBr appears. So our data given to us in the data table is the initial rate of the appearance of NOBr, which is our product. If we look at the reaction coefficients, 1 Br2 produces 2 NOBr. So that means Br2 is going to disappear at half the rate that NOBr appears. So the rate for NOBr in experiment 1 is 3.24 times 10 to the negative fourth, which means that the rate of the disappearance of Br2 equals 1/2 the rate the appearance of NOBr, which is 3.24 times 10 to the negative fourth. So this gets us a final rate of Br2 loss of 1.62 times 10 to the negative fourth moles per second. So that matches our unit given to us up here. Part B asks us to determine the order of the reaction with respect to each reactant, Br2 and NO. In each case, explain your reasoning. So what we're going to do is we're going to compare some of our experiments. So we're going to start by comparing experiments 1 and 2, which will get us the order of the reaction with respect to Br2. So I'm going to compare experiment 1 to experiment 2. So we know that rate is going to be equal to, I'm going to jot down our just general rate law. So rate is going to be equal to K times the concentration of NO raised to a power X times the concentration of Br2 raised to the power Y. So my rates are 3.24 times 10 to the negative fourth. And then 6.38 times 10 to the negative fourth. So that will equal K times, in experiment 1, my initial concentration of NO is 0.0160. My initial concentration of Br2 is 0.0120. In experiment 2, I'm going to have K equals 0.0160. And then my initial concentration of Br2 is 0.0240. So my K's cancel and my concentration of NO's cancel. So then what we end up with is we are going to divide our rates of our reactions, which looks like it should be approximately 1/2. I'm going to check that just to be sure. Yep, it's 1/2. So it's 1/2 equals, we're going to end up with 1/2 raised to the power Y. Therefore, Y equals 1. So it would be first order with respect to Br2. You could also do this just by looking at it qualitatively without actually doing the calculations, and you could say that the rate of the reaction doubles when the concentration doubles for Br2, therefore the reaction is first order with respect to Br2. I personally like to calculate it. Okay, so now we need to figure out the order of the reaction with respect to NO. So we're going to compare reactions 2 and, or experiments 2 and 3. So experiment 2, we know that our rate is 6.38 times 10 to the negative fourth equals K times 0.0160 raised to the 1, because we now know that it's first order. Oh, nope, sorry. That's still X times 0.0240 raised to the 1 divided by 6.42 times 10 to the negative fourth, which gets us K times 0.0320 raised to the X times 0.0060 raised to the 1. So those are using my initial concentrations from my table up above. So comparing my rates gets me 1, dividing those two numbers, and then my K's cancel out, and we end up with 1/2 raised to the X, because 0.0160 divided by 0.0320 gets me 1/2 times 4. Solving for X, divide both sides by 4. we end up with 1/4 equals 1/2 raised to the x, therefore x equals 2. So this is second order with respect to NO. Part C asks us to write the rate law that's consistent with the data and then calculate the value for the specific rate constant K and specify units. So I'm going to skip part 2 of C because that's just plugging numbers in to calculate for K. So you'd pick an experiment, plug all the numbers in and solve for K as your variable. But we are going to go ahead and write the rate law. So I'm going to set my generic rate law I already wrote. So my specific rate law would be rate equals K times concentration of NO squared times the concentration of Br2. Part D gives us a mechanism. So it says that the first step is slow and the second step is fast. And it asks, is this mechanism consistent with the experimental observations? So in a reaction mechanism, the slow step is what's going to determine the rate of the reaction. And so since it's an elementary reaction, the coefficients become your exponents. So the rate for, or the rate law for this slow step would be rate equals K times Br2 times NO, which means that it's first order with respect to both Br2 and NO. So it is not consistent with our experimental rate law. Our experimental says it's second order with respect to NO and first order with respect to Br. But this this mechanism says that it's first order with respect to both reactants. And that's because our rate law is determined by our slow step. Our slow step is an elementary reaction, and we can use the coefficients in our elementary reaction to write our rate law.